Before moving on to a practical example, I want to talk about sRGB, a little bit about gamma, and what that all means. So, sRGB, this stands for the standard red, green, and blue. And this was invented when HP and Microsoft created this cooperatively in 1996 to be used on monitors, printers, and the web. Their whole idea is that they made a bunch of different monitors, printers, etc., and they wanted all of these monitors to have a similar color profile so that color was displayed accurately across all their devices. And so the idea with sRGB when this was designed is that they want a very accessible color space for all sorts of different qualities of TV screens and computer monitors to have access to. In addition to that, they wanted to have a color space that didn't require huge file sizes. And so because of that, sRGB made it very easy to store a bunch of colors without letting the file sizes get too crazy. For one, sRGB represents a color space, or a gamut, or a color profile. All of those words mean about the same thing, or basically the same thing, as far as I can tell. It's a color profile which is defined by the location of the color primaries along the CIE diagram. So remember, this whole thing is CIE diagram. It represents all the light that our eyes can see, and we are just taking a portion of that. So the primaries are where we draw out the corners of this triangle. So this represents absolute blue, absolute green, and red for sRGB. Also, fun fact, it only contains about 36% of the colors that our eyes can see. So remember how I said they want to keep the file sizes low? Microsoft and HP, they wanted to make this easily displayed across all their different monitors. Well, that's why it only contains 36% of the colors we can see. Because it's using less information, it made it easier for them to achieve those goals. sRGB is also known as a transfer function. In other words, it transforms scene-deferred colors, that's the original colors that, let's say, a camera picks up, into something our monitors are designed to show us. And it does this using gamma. So whenever we talk about gamma corrections, we're talking about a transfer function. It's again taking that scene deferred, that original information, and changing it so that our monitors can show us whatever that is accurately. So back in the day, not my day, but in the olden times, we had these things called CRT monitors. And the way that this worked is we basically had voltage go through the back here, and it lit up a panel, and that's what gave you an image. Now, the problem with this voltage is that it gave us this curve that we see right here, this CRT gamma 2.2. And what that basically means is that because of the fact that it used this voltage technology, it could not accurately show us scene-deferred colors. If we take a look at this diagram here, on the left-hand side, we have a value of 0, which is black, and 1, which is white. And so what a CRT monitor would do is, towards these middle values, it would have a hard time being bright enough. If this center here, if that represents what the image actually is, then it was down here because of the fact that it had to use voltage. So what they did with sRGB is they said, okay, well, we need to fix that. And we're going to fix that using a 2.2 gamma correction. So that's what this dotted line represents right here. They said, okay, well, we'll just make this inverse curve that the CRT seems to have a difficult time with. And now we are back to center and all of our images look beautiful. Now, the problem is that these days we don't use CRT monitors anymore. However, the tradition still remains. And even though you have an LED monitor, if it's set to an sRGB space, it is going to require this dotted line gamma correction to show you anything properly. So again, gamma, that's what is correcting this original issue. But, you know, that is where all of this basically comes from. And just so that we're also on the same page with what gamma is, gamma affects your midtones. So let's try to take this image right here, and I'll go ahead and create, let's say some curves, right? I mean, if you guys have messed around with Photoshop at all, or whatever, you've probably seen these curves. It's kind of like taking the curves up and doing this kind of thing. They basically just color corrected those CRT monitors like that until they had what they wanted. And so, again, this is going up. That would be like a 2.2 correction or what have you. Going down, the inverse of that is usually 0.454. So for sRGB, it's both of those things. And so that's kind of where this is tricky. When somebody's talking about sRGB, they're saying, hey, not only does this represent where the primaries are, it's also providing that gamma correction. Oh, but wait, it gets even better because we have sRGB and then we have different kinds of implementations of sRGB that are completely different spaces and do completely different things. So this is where things get really confusing. Basically put, I just showed you sRGB and it's made up of two things. It's where the primaries are, and it's also making that transfer function or that gamma correction, right? Well, depending on the implementation of RGB, you may just only be referring to only the gamma. You might be only referring to the transfer function. And this also changes whether or not your file is 8 or 16 or 32 bits. Let me jump into Affinity Photo real fast, and I'll show you exactly what I mean. So here I've brought in an HDR that we'll be using very soon for our scene demonstration, okay? Now, if we go to Edit, or Documents, that is, and we say Convert the Format or the ICC profile. Check this out. This gives us an idea of all the different ICC profiles that can be associated with this particular image. And just so you know, ICC profiles are basically the bits of information that get attached to the image, which transform the space into whatever your monitor is set to be. So it's the thing that's responsible for applying the sRGB, as an example. So anyway, like I said, we have different kinds of RGB. We have Apple RGB, Adobe RGB, CIE RGB. We have all kinds of different things, wide gamuts, and this one right here, sRGB IEC 61966-21. It's a really great name. Basically put, depending on what kind of RGB, it might be, like I said, just talking about the primaries, or it might be just talking about the transfer function. And as a general rule of thumb, the main ones to know about here is sRGB, this linear one, and the Adobe RGB. These other ones, you can take a look at them, you can research them. They all have different applications and reasons why you might use them. But basically, Adobe RGB is good for printing, whereas sRGB is good for most other applications. Now, here's where things get really tricky. And this is not obvious by any means, even when you look this up, okay? We have a 32-bit image. And if you're not sure about the difference between an 8, 16, or a 32-bit image, then check out the link on the screen where I talk about this in my shading course. But basically put, let's go back here to the ICC profiles. Because we're using a 32-bit image, this ICC profile does not get embedded with the file. Instead, the application is going to provide its own transform. So again, this transform does not get attached to the file itself whenever you have a 32-bit image. Instead, the application is that which provides a transform when you open it up in the program. And just to really show this, let's say I want to export this image, and I go over here to EXR. I will not have the option to embed an ICC profile. It's just not part of it because it's a 32-bit image. And so even though, yes, we do have this thing called color profile from name, it is not actually embedded as part of the image. Just to show you the explanation of this, not all image formats support embedded ICC profiles. For example, EXR allows color information to be specified by chromatices. And don't worry about that for right now. But basically put, when we are making this color profile, it's going to tell the application how to build an ICC profile so that you can preview that in your monitor. So again, if this is getting too technical and crazy, don't worry about it so much right now. Just know that linear EXR 32-bit files are not going to have the same effect as a 16 or an 8-bit file, simply because we cannot embed ICC profiles into the pixels directly. So, if I go here to the JPEG, I can actually select the profile that I want to embed right there as an example. And again, that's responsible for making this image play nicely with other devices. Eventually, we'll get to removing these ICC profiles, but for right now, if that's too confusing, don't worry about it. It'll make sense later. I just want to expose you to this right up front so that when we get to it later, you'll know what I'm talking about a bit more easily. But I just want to mention that RGB is kind of confusing because it means all kinds of different things. As long as you remember that this all comes down to transfer functions and the primaries, you'll be able to look up these different profiles and figure it out from there. In the next video, let's talk about LUTs. There's one more piece of information we have to bring together. Hopefully this is not too confusing yet. If so, take your time. Don't worry, this will come together when we actually jump inside of Houdini, and we'll go from there.